All right, so chapter 3, finally getting into the chemistry of things, finally getting past just the math. The next, there's some more calculation stuff that's going to happen here, but a lot of it is going to be more conceptual. So everything that you can see in your room is made of matter. Everything you see in this room, anything that you can see is made of matter. Different kinds of matter are related to the differences between the molecules and atoms that compose the matter. So right, this is clear because it's made of different atoms and molecules than this is, or the whiteboard, right? And I can write on the whiteboard with a dry erase marker and erase it because of the types of atoms and molecules that those are made up of. And so those little tiny pieces, I think that like the car analogy I used, if we can understand those tiny pieces, we can understand why the whiteboard is different from the marker, is different from the plexiglass or acrylic or whatever that is. So I like this shirt. You occupy space, you have mass, you matter. So everything that has occupies space and has mass is matter. Some types of matter are easily visible. We point out like the whiteboard or anything that you can see, right? Easily visible things. Other types of matter are impossible to see without magnification. We're talking like viruses, we're talking bacteria, even like the dust. Like there's dust in the air right now, but we can't see it. Also, the air is matter because it occupies space and it has matter. But wouldn't you be able to see, viruses or dust or even some small mites without magnification? So matter may appear smooth and continuous, but it's actually not. Like this seems really smooth. It's not. It has texture to it. And everything, if you zoom in far enough, is going to be bumpy. Even like the most finely planed, machined piece of metal is going to have variations in the heights of the atoms on the surface. So here's a key. Matter is composed of atoms. Remember, everything you can see and a lot of things that you can't see are made of matter. And if all matter is made of atoms, then everything is made of atoms. These atoms are submicroscopic particles, so you can't see them under a regular microscope. But they're the fundamental building blocks of matter. If you take, so these are the atoms are the individual pieces. I was actually just thinking this morning I need to buy like a small Lego set so I can bring up the pieces because I think Legos are a really good example of atoms.
My kids have a ton, I'll bring them.
All right. They are the worst to step on. So yeah, I think Legos are a great example because you take the individual Lego pieces and they are nothing really, right? They're just blocks, but you can put them together. And if you've ever seen like Legoland and stuff, like the Lego build, what are they called? Buildmasters? Brickmasters? Brickmasters, that's what they're called. They'll build insane things that would just blow your mind out of those same basic individual pieces that you could have at home. And so that's what atoms do. They bond together, they form molecules. Those molecules then form everything. And specifically, the atoms bond together in specific geometric arrangements. So a molecule always has a specific number of atoms and combined in a specific way, kind of like a Lego set. It's like if you had a small Lego set, that set would only be complete if the Legos are all attached in that specific configuration with a specific number of each type. So again, ultimately, everything's composed of matters. Everything is composed of matters, that's what I said. Everything is composed of atoms. In some substances, the atoms exist as independent particles. In a lot of other things, maybe more things than not, they're bound together. So things like metals, the atoms actually exist as individual atoms, but they're able to move around a little bit move around each other a little bit for more malleable metals. That's why metal can dent. For other things, like this isopropyl alcohol, these are the molecules that I was talking about that are bound in specific arrangements. So in each of these, again, actually, does this projector show red? Kind of, a little bit? Okay. I'm a little bit colorblind, so I can't tell which ones are red there. But so for anybody else, this one's red. So the red ones are oxygen. The white ones are hydrogen. This is oxygen, hydrogen. And then the black ones in between are carbon. And so for each of these molecules, there's going to be 3 carbon atoms. There's going to be 7, I think there's 8 hydrogens and 1 oxygen in that specific ratio. And all of these, even though some of them are rotated differently, all of these are bound together in the same configuration, right? So that's like a Lego set. There is a way that you can observe individual atoms, and that's with a scanning tunneling microscope. And it's not observing like you've got lenses. They're, if I remember correctly, shooting a beam of electrons across a surface and then recording how they reflect off of the surface, approximately. So here they show up as these sort of like hills. Reality, they're more spherical, if not perfectly spherical. But because of the way that the electrons are reflecting off or passing through, we get these bumps instead. So you can use scanning tunneling microscope to look at DNA. And this was like one of the things, this is the double helix. Let me see if I can highlight it here. I think that's it there. And there, right? So you get that double helix, whoops. That's the double helix of DNA. And DNA is just a huge molecule. It's a molecule made of molecules. All right, so everything's made of matter. But now we know matter behaves differently depending on what state it's in. Ice, we're going to talk about ice so much in this class. And water, because it's the most relatable material that exists in 3 states that are also relatable, right? We know that we've seen steam, you've seen liquid water. Hopefully you drank some liquid water today, or you do later. Stay hydrated. And hopefully it's got some ice in it if you like ice water. So our 3 common states of matter, because there are more, the common ones that we're going to talk about are solids, liquids, and gases. We've seen water in all 3 of those. Other things can exist as solids, liquids, and gases as well, though. Actually, I would say anything under the right conditions could be a solid, a liquid, or a gas. So in the solid state, solid matter, the atoms and molecules are packed close to each other. And they're packed so close that they can't move. So if you think about, again, well, it'd be kind of like being in like the front, like right in front of the stage at a concert, right? Everybody is so packed in that you can't move around unless you're the mosh pit. And that's why things that are solid don't just like drip or melt off of the surfaces that they're on. Those atoms are all so stuck together that they don't move. They do vibrate or oscillate, just like you would at a concert. Everybody's trying to dance with the music. But they can't get any farther than that. And because of this, solids have a fixed volume and a rigid shape. All right, so those are the key takeaways here. Solids have a fixed volume, rigid shape, because everything's locked together. There are 2 types of solids. I think we'll get into this more later in the class. There are crystalline solids, which are atoms or molecules that are arranged in patterns with a long-range repeating order. So if you look at any section of a crystalline solid, it will look identical to the other sections. And you'll be able to see, because the human brain is super good at recognizing patterns. Right, if we look at this, you can see that these are arranged in a sort of pattern. You might not be able to recreate it, but you can see that like those are all lined up, right? Other types of solids are amorphous solids, where the atoms are just kind of lumped together. There's no organization to them. They're kind of packed messily together. This is like crystalline solids are like when my wife packs. It's very organized and everything's in its spot. And then the amorphous solid is when I pack and it's just like, I want these clothes, and I just throw them in. All right, so liquid state is like the end of the concert. So now everybody is like trying to leave. There's a little more space because people have started to leave. And you can move around a little bit, but you're still kind of in touching distance of everybody. And so in liquids, again, they're close. The atoms or molecules are close to each other, but they're free to move around and by each other. So you can get around and by people. You might have to fight them a little bit, but you're able to move now. For liquids, they have a fixed volume because the atoms and molecules are in close contact. But now they assume the shape of their container because of that free movement, right? So the crowd of people is the liquid. They're conforming to the shape of the like aisles and the exits to try and get out. So liquids, let's see what's on the next slide here. No, we go straight to gases. So liquids, have a fixed volume. I want to like phrase this just like this. Fixed volume and an amorphous or maybe malleable or, they don't have a rigid shape. They have a liquid shape, which is terrible, right? They're amorphous, so they can change their shape to fit the container or to match the container that they're in. It's trying to make it more one-to-one comparison with solids. For gases are like the people out in the parking lot going to their cars. So once you've gotten out, now you're no longer really generally trying to be as far away apart from as anybody as possible because you're overstimulated because you've been packed against them the whole night. And they go out and you just sort of fill the parking lot with people, all spaced out. Gases are just like that. The atoms or molecules are now separated by large distances and free to move relative to one another, right? So since the atoms and molecules that compose gases are not in contact with each other, they are compressible. So you could take all those people and sort of like herd them back together into one area, and then as soon as you remove the barrier, they'd spread out again. Gases will do the same thing. And this is like why you can get high pressures in like a car or a bike tire. We're compressing those gases into a smaller space. And the gases always assume the shape and volume of their containers. I think the better analogy for this one is that if you ever cook with garlic or something in the kitchen, that smell is a gas, and it will spread throughout the entire house eventually. It might take a while, but it will get to every single part of the apartment or house or whatever, or room at least. And so that's the gas assuming the shape and the volume of its container. These are the words I was looking for. So this is the table that really does compare all of them. And again, this is not something where I want you to, this is a recurring theme in chemistry. If you can understand why things happen, you do not have to memorize what happens. So it's better to understand, to take this back to chapter 1, better to understand the theory than it is to just memorize the law. So why do solids have a definite shape and a definite volume? Because the atoms and molecules are so packed together, they can't move around. And they also, because they can't move around, right, that gives them a definite volume, definite shape, and they're incompressible. So you can't squish them any closer together because they're already as close together as they can get. For liquids, right, why do they have an indefinite shape but a definite volume? Well, they've got a little bit more room. So they can move around each other, but they can't get farther than like arm's length from each other. They're still stuck, but able to move. So indefinite shape, definite volume. And then gases, because they're so far apart from each other, they have an indefinite shape. So they'll take the shape of their container, they'll fill that container, but you can also compress them because there's empty space between them. Cool. All right. Changing gears here again a little bit. So now we started by talking about like everything's made of matter. All matter is made of atoms or molecules. Then we took that idea of matter and we said it can be solid, liquid, or gas. So we've got three different types, three different phases that we can have for matter. And now, instead of classifying it based on whether it's a solid, liquid, or gas, we're going to look at classifications of matter that depend on its composition. So what is making up that matter? And this is one that you can kind of look at as a decision tree. So our first big classification is going to be pure substances. So those are only one type of atom or molecule. And then mixtures, which are composed of two or more different types of atoms or molecules. So if you had pure water, like reverse osmosis water, which is probably as pure as you're going to get, that is all just water molecules if your reverse osmosis is working. But something like, for some reason, Gatorade is the thing that comes to mind. Right? Gatorade's got sugar in it, it's got electrolytes in it, it's got other things. That's a mixture of different types of atoms or molecules. Oh, good. We start right off with this tree. So this is how we can sort of take things and we could say, does it fit into this category or that category? And then we've got subcategories under those. And we're trying to sort of take all of matter, which is a lot to deal with, it's everything to deal with, and put it into smaller and smaller boxes. So you can say, okay, we can deal with this matter that's all like this, or all of the matter that's like this thing over here. So our first one was pure substances or mixtures. All right, so all of matter can be broken down into these two. And then we can break that down farther, and those are the following slides. So we'll work our way through this, looking at all the different, or these 4 different boxes that we can sort of put matter into. So our first one we're going to talk about is a pure substance. So that's, again, down the left side of this tree. We're in pure substances and then elements. Elements are a pure substance that cannot be broken down into simpler substances. So all the stuff on the periodic table of the elements. All right, so those are the simplest elements. Once you get them to just carbon or just nitrogen or just oxygen, you can't break it down farther into a smaller thing. Yeah, I don't think there's anything else to say about that. So those are the elements. Those are the purest of pure substances. The next one here is a compound. And so go back over to this table. Compounds, so we went pure substances, We talked about elements. Now we're going to talk about compounds. So a compound, again, is a pure substance composed of two or more elements in fixed, definite proportions. So these are the molecules, right? So this is something made up of all of a single type of molecule, right? So for each of those molecules, it's like the Lego set, right? It's got a certain number of each type of atom. And then the compound is made up of a bunch of those Lego sets or a bunch of those molecules. These are going to be more common than pure elements. And they can be decomposed into simpler substances. So if we took something like, well, the easiest one to draw is water. So I'm going to draw water. So you have water, which is oxygen and 2 hydrogen atoms. Right? That water molecule is made up of oxygen and hydrogen. Oxygen and hydrogen are elements. So we could take this water and break it down into the simpler substances that make it up. But in pure water, in a pure compound, it's only going to be water molecules. I like that these are on the same slide. So then a mixture, so this would be going to the other side of the tree now. Mixtures are combinations of either compounds, different compounds together, or different elements together, all mixed. And unlike a compound, your proportions can vary. So this is kind of like if you have, well, let's say if you had just water, that's your, so say we have a glass of water, and it's pure water, reverse osmosis, the finest. And that would be a pure compound. But we can add sugar to it. So if I put sugar into here, sugar is by itself also a pure compound. But if I mix those two together, say I put in 1 gram of sugar, now I have a mixture. And the proportion isn't fixed, because I could add another gram of sugar, or I could add, any amount of sugar, and it would still be a mixture in varying proportions. And it would be a little bit difficult, but we could technically separate the water out and the sugar out. So most things are mixtures. Air is a mixture of nitrogen, oxygen, carbon dioxide, and other gases. Seawater, of course, is a mixture of lots and lots and lots of different things. You'll even get a mixture of things in the sand on the beach. So now we're going to take mixtures. We talked about elements, compounds. Mixtures can be broken down further into types of mixtures. And these two categories there are gray areas between them. So when I'm talking about a homogeneous mixture or a heterogeneous mixture, it helps to think of a fixed, like 1 cup. So like if you took a cup of something, is it going to be heterogeneous or homogeneous? And I think you'll see why in a second, and I'll explain why in a second. So a homogeneous mixture, not homogeneous, that's a different thing. Homogeneous mixture has the same composition throughout. So if I have Gatorade, right? I'm going to use this Gatorade example a lot. Okay, didn't want me to write that. Gatorade. So if I have a Gatorade, when you're looking at the Gatorade, it's going to look like it's the same thing all the way through. Hopefully there's nothing floating in it or settled to the bottom. So it's the same composition throughout that whole Gatorade. An example of a heterogeneous mixture then would be like orange juice with pulp. So if you've got like high pulp orange juice, which I do not like, but that is going to be heterogeneous because there's pulp in some parts of it, and it's not going to be like every sip you're not going to get the same amount unless you're really shaking it beforehand. Where this gets a little bit hazy is if you think about Okay, is the ocean a homogeneous mixture or a heterogeneous mixture? Depends on how much of the ocean you have. If you think of the ocean as a whole, heterogeneous, right? There's fish in it. The composition is varying throughout the entire ocean. But if I go and I get a cup of seawater, it's probably going to be a homogeneous mixture inside that cup. So that's why it gets a little bit hazy. So if you think about all of these things in terms of like a cup. Anybody have, can anybody else come up with an example of a homogeneous mixture? Something where the composition is the same throughout. Tea? Yeah, tea. Might have to specify tea without ice or tea without a lemon in it. But yeah, so like tea or coffee, unless you go to Starbucks and you get like a macchiato or something, and then it's going to be heterogeneous until you mix it, which I think it was a TikTok where they had like the lids, the strawless lids. She has to mix it, so she like holds her mouth over it and then like. So yeah, so like tea, coffee. Again, unless it's like the Starbucks coffee. So I'm talking about when I give you a question like this on the exam, because there will be a question like this on the exam. Think of like the simplest thing. I'm not trying to like, ooh, is coffee homogeneous or heterogeneous? And you're like, it's homogeneous. I'm like, psych, it's a Starbucks caramel macchiato. Not doing that. So I know it's hard, but try not to overthink it. What about a heterogeneous mixture? Yeah, it depends on how you make it, right? So if you have that sugar at the bottom, lemonade could be heterogeneous or homogeneous. Anything that would be indisputably heterogeneous. Yeah. Mud? Yeah. Okay, I could roll with mud. I think like you could have like, again, if there's like rocks or stuff in the mud, or like you get like really, 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 a smoothie. Smoothie is good, depending on how well it's blended. Huh?
Beer.
There's a whole bunch of different kinds of beer. I think beer, for the most part, would be homogeneous.
What about like IPAs? Beer and IPAs and seltzer.
Oh, so inside of each of those individual things. So I think one of the ones is like chicken noodle soup or a stew would be homogeneous.
What about oil and water since they can't mix?
Ah, yes. So a heterogeneous mixture, oil and water. So if you just had water or you just had oil, those would be homogeneous. If you put them together, though, in the same cup, that would be heterogeneous. Inside that cup, the mixture changes throughout. Cool. All right, that is, oh good. And then we can do this question when we come back. 9:45.